you have the curve, negative 8x squared plus 5xy plus y cubed equals negative 149. Hopefully everybody knew that what you were going to have to do to answer part A is what? What do you need to answer part A? You need implicit differentiation. And it's not a related rate problem. We're not talking about finding the derivative of y with respect to time. We're talking about finding dy dx. So x you can do normal, y you have to do it implicitly. Okay? That's why with related rates, when it was with respect to dt, every variable you had to do implicitly because there was no time variable. Okay? All right? So get this, we're going to get negative 16x plus. Now, Danny asked me this the other day, and I think it's a very good question. How do you handle product rule when there's a coefficient out front? There's two ways to do it. All right? You can take the 5 and treat it as being a part of the x. But you need to see the reason we're using product rules, not because of the 5. It's because of the x times what? Y. It's because of two variables being multiplied. That's how you know you use product rule, is when two variables get multiplied together. Okay? If ever you got two variables multiplied together, that's when you're going to need the product rule. So I'm going to leave the 5. What I do is I just put the 5, and I just leave it out front because constant multiple, if you remember, a constant times a function, ddx of a constant times a function. Hopefully some of you are actually getting what this rule really does and how powerful it actually is you can just take the constant times the derivative of the function. Well, in this case, since it's a constant times a product rule, it'll just be the constant times the product rule. So I'm going to do the product rule with the xy and not worry about the 5 right now. So derivative of x is 1 times y plus x times dy dx. And then distribute the 5. Now some of you are like, well, that's not a big deal to me. I can just bring the 5 with the x, and then it'll already be distributed. I don't care which way you do it. Just I like to treat it separate because to me, it makes my product rule really simple to think about. And sometimes I forget the number is why. And it'll happen to you too. So plus 3y squared dy dx. Does anybody know why I use dy dx and not y prime? Sometimes those primes start to look like ones, or some of you write light enough that your primes kind of disappear. It's magic. It's crazy. I can't even believe it happens. But it does, and the primes disappear, and all of a sudden that y prime turns into a what? A y, or a y to the first power. So dy dx, you're not going to confuse. Okay? Equals 0. Now what's the next step? Yeah, simplify, get the dy dx to one side. And I don't care. At this point, guys, right now, you just got a point. Whenever you do an implicit differentiation problem on the AP exam, if it's on the free response, you get a point for initially showing the implicit differentiation step. The rest is algebra, and they don't care how much work you show. You can do it all in one step if you want. You can say, I'm going to distribute the 5, I'm going to move the 16x over, I'm going to move the 5y over, so that's going to be a positive 16x minus a 5y. I'm going to factor the dy dx out. I'm going to end up dividing by x plus 3y squared, and voila, I give the answer just like this. And that's acceptable. I didn't show any steps. They know you had to know all of it.
Is it a 5x or 5y on top?
Is that a 5x or a 5y? I think it's supposed to be a 5y. And that's it. Done. Pretty simple, right? That would have been about 2 or 3 points.
Whatever happened to the 5x on the bottom? Like 5. It's just x plus 3y squared. What happened to the 5 there?
Yes.
Sorry.
I was getting cocky. Like I said, anybody can forget something. Even me. All right, 16x minus 5y over 5x plus 3y squared. Any questions? So that's probably worth 2 points. So kind of see how you would have done 2 points. And the goal is to get, if you can get to like 8, 9 points, you're like in the 5 range on that problem. Now people are like, what happens if I get 8 or 9 points on one problem and only 2 or 3 points on one problem? Well then hopefully by the end of the whole free response you average around 6 to 7 points because that's around the 4 range. You average around 5 points on a free response, like getting half of the free response, basically averaging half, it's about 3. A 3 passing on the AP exam is only about a 40%. 40 to 50%.
As long as you pass.
Well, no, it just should show you how flipping hard it is. It should tell you, it's hard. Okay, it's not easy. There's a lot of math teachers. I guarantee you, if I gave the AP Calc exam to Mr. Knutson, Mr. Rice, Mrs. Rosenell tomorrow, maybe Mr. Rice might, just because he's been in college freshman, I guarantee you they probably wouldn't pass it. In fact, I know they will. I know Mr. Knutson will. Get like a 1. Okay? You got a 1 going on. And if I took the AP stats on tomorrow, I'd ace it. But anyways, write an equation for the line tangent of the curve at 4, -1. What do you need to be able to write an equation for the tangent line? I also have my master's in math and they don't. Actually, I would not pass the AP stats exam. I know I wouldn't tomorrow.
80 points.
I'd probably get a 2.
You need slope.
You need slope and the point. So you have the slope, or the point, don't you? What's the point?
4, -1.
4, -1. Now, if you did not have the point, let's say they just gave you the x value, what would you do? You'd have to plug the x value back into the original, which I don't like that because there could be more than one point. So like if you plug 4 in for x, there might be more than one y, so they just gave you 1 point, which is kind of nice. It's like I only have to find one tangent line. But just understand, with implicit differentiation, if they just give you the x, there might be more than 1 point, which means there might be more than one tangent line you're having to find. So it'd probably say, write the equation for the tangent lines at x = 4 if they just give you the x. But this one they gave us just 1 point, so there's only one tangent line we're trying to find. We also need the slope. Where do we get that? Derivative. So I'm going to find dy dx at 4, -1. So I'm going to plug 4 in for x, so that's going to be 16 times 4, and then -5 times -1, all over 5 times 4, plus 3 times -1 squared. 64 plus 5? 69 over 20 minus 3. 20 plus 3. So that'd be 23. Thank you. I'm all over the place today. So that'd be 69 over 23. And does that end up being 3? So it's y plus 1 equals 3 times x minus 4. Done. All right, I love part C. Part C. There is a number k, so that the point on the curve, 4.2 comma k, is on the curve. Thank you for telling us that. So there's a number k such that 4.2 comma k is on the curve. All right? Use the tangent line found in part B to approximate the value of k. This is called, ready? This is called, whenever you do this, this is called tangent line approximation or local linearity approximation. What it's doing,
Why can't you just plug 4.2 into the original equation?
because they don't want you to.
They want you to approximate.
They want you to use the process of what if you didn't know the original equation? What if all you knew was the tangent line? Well, the tangent line, let me show you, is a very good approximation. Let's say you had the point 4, -1, okay? 1, 2, 3, 4. And all, because you're going to take a class in college if you go into engineering. Are you thinking about engineering still? Okay, then you're not going to get this gift. You're going to take a class called differential equations if you go into engineering. In engineering, they don't give you equations of y. All the equations you deal with in differential equations are derivative equations. So you never know the original equation. You only know the derivative. So you're doing a lot of this approximating. The whole class is based on trying to go back and solve for y.
What was if you just find
We
the old
touch
derivative?
differential equations a little bit in this class. What?
What was if you just find the old derivative? Or like the original?
Original, only about 75% of differential equations can be solved. So 25% of differential equations, and it's not the exact statistics, but only about 3/4 of differential equations can actually be solved for the original. So there's still a quarter out there that have never been solved by mathematicians. They can only be done by computer. Now, let's say the curve looks something like this. It's probably a circle kind of looking thing because it has x squareds and y cubes and all kinds of crazy crap. And let's say it looks like the tangent line has a slope of 3, so the tangent line looks like this. Ready? Follow me here. I'm going to actually try and make this a little bit better. And let's say tangent line is about like this. You with me still?
Yeah.
Let's say you did not know that original equation. Still, this sucks.
So instead of the original equation, they would just give you
make this perfect. Yeah, they would give you dy dx. Okay, so let's say the original equation looks something like this, a circle kind of thing. And you bring up a good point. Why not, if we know the original equation, why not just plug 4.2 into the original equation? Because if you went to 4.2, I don't think it'd be too hard to find. 4.2, actually the original equation would have to go back that way. I'm sorry, I totally biffed this. Go with me here. I'm going to do red for the original, okay? You with me? Let's say original equation looks something like that. You still with me? And here's the tangent line at 4. In the original equation, if I was to find the point on the original equation, if I was to go over to 4.2, it might be right here, that point. Well, tangent line approximation ends up being good approximating. If you're close, which means local, if you're close to the actual point of tangency. Is 4.2 pretty close to the point of tangency? Like, you don't want to be out at 16.
Yeah.
16 wouldn't be close to 4. I mean, 16 would be stupid. Because you don't know what the rest of the equation's going. It might go up and back down. Like, for example, this curve might go like this. So if you're out here at 16, that graph probably doesn't approximate very well at all. Okay, it might just by chance, but it probably doesn't. See, what you're going to use, look how close this is. Now the y value, here's at -1. It looks like if the 4.2, if you're on the tangent line, those points are fairly close to being the same. And my graph really sucks. They're probably even closer than that. Okay? And if we actually plugged in the actual value, we can figure it out. So the tangent line is used to approximate what the actual y value or what the actual point would be on the graph. It's called tangent line approximation. And literally all you do, I want you to think about how easy this is. All you do in part C is instead of plugging in the value to find k, instead of plugging into the original equation, which gives you the actual y value, you plug it into the tangent line to get an approximated y value. That's it. All you do is take 4.2 and plug it into the tangent line you found in part B. And they literally have that on the exam every year. Okay, so what you're going to do is take your tangent line equation, and we're going to use the tangent line to approximate the value of that point, even though we could get the actual value by plugging in the original. So it'd be like this. So it'd be y plus 1 equals 3 times 4.2 minus 4. What is 4.2 minus 4? Do this without a calculator. 3 times 0.2. What's 3 times 0.2? 0.6. So you have y plus 1 equals 0.6. Subtract 1, what do you get? -0.4. There it is. I bet if you plug in the actual, I bet it's within 1/10. I bet the actual was so darn close to that. It doesn't look like it on my graph because my graph sucks, but I bet you that that tangent line came really close to being the actual point.
It is negative.
So it is? Oh, you do it the next part. It says, Ryan, oh, you do it? Use the tangent line found in part.
Negative 0.37.
Negative 0.37. So write an equation that can be solved to find the actual value of k so that the point on 4.2 is on the curve. So what do you do in part D? Plug it into the original. So if you plug it into the original, now they're just comparing the actual value with the approximated value. So, gosh, this is really good for you guys because this, I don't usually see them actually plug in to find the actual. You're just supposed to understand that it approximates the actual. So I like this because we're connecting it. So now we plug into the original the 4.2, which would be -8 times 4.2 squared plus 5 times 4.2 times y plus y cubed equals -149. And if you solve this equation, you would get the actual value. Now, they didn't even ask for you to solve it, did they?
Yeah, I did.
No, they didn't. It just says write an equation that can be solved.
And then for E, they have to solve it.
Oh, they actually asked you to solve it. They write out.
So you can plan.
So what do you get? What's this junk here? -8 times 4.2 squared.
Negative 141.12.
What is it?
Negative 141.12.
1, 2? All right, what's this? Huh?
21.
21y plus y cubed equals negative 149. Yeah, and maybe some of y'all change those over to actual k's, because that's what the k values representing the y value. Whatever, that don't really matter. Then we add this over, so we're going to get, no, I wouldn't add that over. I go y cubed plus 21y. I'd add the 149 over. What's that going to give you? 7 point what? 88 equals 0. How do you solve it now?
Quadratic formula.
Can't use quadratic formula. It's not quadratic formula. It has to be power, half the power, no power.
Oh, I didn't know it was a third.
So what do you do?
I don't know.
Take out your calculator, go to y equals. Quick, I want to talk about this because there's more than one answer here, or might be more than one answer. Plug it into y equals. I hit zoom 6 real quick. This is the last one we're going to do. I'm going to tell you about class today. Hit graph. What do you do? I'd hit zoom 6. Why zoom 6? What are you going to do? What are you looking for? Where that graph crosses the what? X-axis. How do you do it? Second trace, 0. Guys, you set the equation equal to 0. Anytime you set an equation equal to 0, you're just looking for that, to solve it, you're just looking for where that equation crosses the x-axis. So what do you get?
Negative 0.37.
Does it cross the x-axis ever again?
I don't know.
No, you know. I'll tell you how you know. It's y cubed. Y cubed goes up at one end, down at one end. It looks like it shoots up, doesn't it?
Yeah.
Looks like it shoots down. So y cubed can either cross the x-axis once, and then the other two roots are imaginary, or it can cross 3 times, and there can be 3 rational or irrational roots. It's only crossing once, so the other 2 roots, because y cubed has 3 solutions, but the other 2 are imaginary, so you don't worry about those. So, there it is. How close were we? So the tangent line does approximate. And when you're close, it's called local linearity. And the reason they call it local linearity is because you're using a line to approximate a curve. So close line approximation. That would be the dumbed down version. Close line approximation, local linearity approximation, or tangent line approximation. Okay, pretty cool, isn't it? Answer some good questions today. You learned something new. That is on the exam. And those are give me problems. All right, today I am not going to be here.